Hello everybody. Hi. Am I visible? Am I audible? Give me a quick good to go. Hello everybody. Can you see me? Can you hear me? Am I visible? Am I audible? Tell me quickly. Yes, you want the notes, the first part of the notes, second part of the notes, everything is going to be discussed with you, shared with you. Can you see me? Can you hear me? Give me a quick good to go, very fast. We have the second part of binomial theorem today, and I want to dive into it ASAP. Am I visible? Am I audible? Everybody, a quick good to go. Give me a quick thumbs up if you can see me clearly, hear me clearly. Is the video and audio perfect? Absolutely perfect, pitch perfect to the T. Tell me quickly. Yes? Yes, ma'am? No, ma'am? All good? All set? So today is the second part of binomial theorem. I will be sharing with you the notes very quickly. But make sure you stick through this session from start to end. It's not going to be super long like the first part because we have 2 to 3 topics to be discussed here. But these topics literally can make or break your score. When I talk about binomial theorem, you already know it's one of the highest weightage chapters in your JEE Main exam. But having said that, the topics that we will discuss today specifically are those topics which happen to be slippery area for students. They happen to be slippery area for students. Students slip on these topics a lot. And this is where JEE Main loves to spread a trap for you. By asking questions from the topics that we will discuss today, JEE Main wins and student loses. These topics actually happen to form questions which act like traps for you. And you tend to get stuck in the trap, which is something which will no more happen because now you are in my hands. Now you are in my support, under my guidance, under my mentorship. So this is not going to happen anymore with you. Today I will be discussing with you, number 1, results on binomial series, supremely important, and how you have to identify that, okay, this question happens to be solved by the results on binomial series. This question happens to be looked from this perspective. This question happens to be solved by this approach. So this, judgment of number 1, question selection, and number 2, deciding what approach to follow to crack the question is something which is a knack. It's a skill, people. It's a skill, and you have to polish this. You have to master this, excel at it. Okay, and that is going to happen in today's class. After this, we'll talk about multinomial theorem and so many questions, beautiful type of questions based upon it. And also, I will discuss with you something called greatest coefficient. So, can I get started, everybody? Are you guys excited to learn about all these topics because they happen to be sensitive areas when it comes to students. They happen to be areas from where JEE Main asks questions just to lay a trap for you. That's for sure. And my students will not fall in the trap. My students will not get stuck in the trap. They're going to sail through the trap. Yes, we are students who live by a different meaning of fear. See, I do understand you're very close to your exam, and right now, yes, you're fearful. Yes, you're scared. Yes, you're anxious. Absolutely, you are completely engulfed in overthinking. I know all of this. But there are 2 meanings of fear. Number 1, FEAR, forget everything and run. So you're so scared that you kick your dream away and you just run away. I don't want to do this. I give up. That's it. I'm running away. Number 2, FEAR, face everything and rise. Whatever the difficulty, no matter how hard the journey seems, we're going to fight it through and come out stronger like a warrior, like a phoenix. So which definition of fear do you wish to live by? Do you wish to follow? Which one do you think is going to help you achieve your dreams? Tell me, is it forget everything and run, or is it face everything and rise? Rise above your fears, rise above your insecurities, rise above your second guessing yourself. We have to rise above that. Isn't it? That's the aim, people. See, JEE journey is not just about cracking an exam. It's about becoming a best version of yourself. It's about actually, unlayering your own self and coming out like a warrior. Okay? So welcome everyone. Hi Navansh. Hello Working Hard. Hi Esbaradi. Do not worry about the notes. Please don't worry about the notes. Don't forget to join the Telegram group, which is Study with Bhoomika Ma'am. Okay, quickly join the channel, because this is where I share the notes, this is where I share the link, this is where I'll be sharing loads of questions with you, which I do not discuss in my live sessions, but I do share on the Telegram group, which are probable to be asked in the paper. So not all the questions I can discuss on my session. I do discuss plethora of questions, but some questions here and there which I do feel really are a must solve for students, and these questions can increase the chances of students excelling in the exam, I share on the Telegram channel. All right? Yes? Okay, Navansh, this is part 2 for you. So without any further delay, let's get started, guys. Let me tell you, and you have to listen to me very carefully. Attention JEE aspirants. NTA loves to ask questions from results on binomial series. But fact of the matter is that students find this topic very scary. They slip on the questions, they lose marks. But hey, Bhoomika Ma'am to the rescue. I will be sharing with you 7 powerful results which you have to master, because questions from here can make or break your score. So listen to me. Number 1. MCR plus M plus 1 CR plus M plus 2 CR and so on till M plus N CR. This is equal to M plus N plus 1 CR plus 1 minus MCR plus 1. But this minus quantity comes only when M is greater than equal to R plus 1. Otherwise, it's absent. Second, summation R NCR is equal to N into 2 to the power N minus 1. Summation R square NCR is N plus 1 2 to the power N minus 2. Next, summation NCR upon R plus 1 is 2 to the power N plus 1 minus 1 upon N plus 1. Number 5, summation NCR whole square is 2NCN. Next, summation R NCR whole square is equal to N square into 2N minus 2 CN minus 1. Last, summation R into NCR whole square is N into 2N minus 1 CN minus 1. Learn them, practice them, and thank me on the exam day. Okay, these results are what I will be proving for you in today's class. These are the results which I want you to master. These are the results which we are going to internalize and make it a part of our system. All right, let's go. I'm super duper excited. Let me show you and discuss with you the first result, how actually it works, how is it derived, how do you apply it in the questions. What is the first result? I just said it out loud. I'll be writing it for you. It says MCR plus M plus 1 CR, M plus 2 CR, and so on till M plus NCR. Okay, this is equal to M plus N plus 1 CR plus 1. So see, you are going till M plus NCR and the answer is coming out to be plus 1 upar and plus 1 niche. So plus 1 above, plus 1 below. Whatever is the highest upper index and highest lower index in your entire trail of series, in that highest binomial coefficient, you add a plus 1 above, plus 1 below, and that is what you are getting on the right hand side. M plus N plus 1 CR plus 1 minus MCR plus 1. As I said, this minus MCR plus 1 quantity comes only when M is greater than equal to R plus 1 or R plus 1 is less than equal to M. Got it? If your R plus 1 is less than M, or rather greater than M, if your R plus 1 is greater than M, then your answer is just M plus N plus 1 CR plus 1. Because you know, as a matter of fact, that your NCR is well defined only when R is less than equal to N. Then only this NCR is a valid quantity. It gives you a valid answer, a well-defined answer. It's an acceptable quantity. If your lower index is greater than the upper index, this NCR makes absolute no sense. Similarly, if R plus 1 is greater than M, MCR plus 1 makes no sense. The value of it simply becomes nothing. It's a 0. And that is why it's absent from the next quantity. Got it? Cool. But question arises, how can I remember this? How do I internalize it in my system? How actually do I make it a part of my memory? And for that, I will be discussing with you a beautiful, smooth proof. So let's start. Let's start, people. Everybody ready with your pens and notebooks? Very important. Make sure you understand each step of how I am deriving this result, because when you understand the derivation, applying this result in questions becomes a cakewalk. It's super easy. It's like walk in the park, easy peasy lemon squeezy. So let's start. When I talk about MCR, guys, very careful. When I talk about MCR, what is this? This is coefficient of x to the power r in 1 plus x to the power m. Right? Very simple. Stop me whenever you feel that you are not understanding. MCR is coefficient of x to the power r in 1 plus x to the power m. Very easy. What about m plus 1 CR? This is again coefficient of x to the power r, but in the expansion of 1 plus x to the power m plus 1. What is m plus 2 CR? It is again coefficient of x to the power r in the expansion of 1 plus x to the power m plus 2, and so on. The last quantity is this, which is coefficient of x to the power r in the expansion of 1 plus x to the power m plus n. That means this entire series which is written on the left hand side, this is nothing but coefficient of x to the power r in this complete sum of series. Yes or no? Yes or no? Correct? If I write this series, this series, this series, and so on, this series, and from each series, I collect the coefficient of x to the power r. Eventually, I add all of them. What I will end up getting is my left-hand side expression that I have to prove, solve. Yes? Cool? So, this makes sense till here. Now, what is this? Do you know what is this? It's very simple to decode. This is nothing but a GP of how many terms? M, then m plus 1, then m plus 2, and so on, m plus n. From m plus 1 till m plus n are n terms, and right in the beginning there is another term written which is more like m plus 0, right? So n plus 1 terms. Yes or no? N plus 1 terms? Yes. Now, how to solve this? Simplify this. Come on. A, r to the power number of terms. R is the common ratio, which is 1 plus x to the power number of terms minus 1 upon r minus 1. So 1 plus x minus 1, this gets cancelled out. You are only left with x. So you want coefficient of x to the power r in this expansion, guys. You want coefficient of x to the power r in this expansion. But hey, here's the catch. Already an x is written over here. So if you want coefficient of x to the power r from this entire expansion, equivalently I can say that I want coefficient of x to the power r plus 1 in the numerator expansion, right? Because this x is sitting in the denominator. So from the entire numerator, I want the coefficient of x to the power r plus 1, so that that part upon x will give me the coefficient of x to the power r, because below x and above x, 1 x will cancel out. Correct? So this means equivalently I want coefficient of x to the power r in numerator. 1 plus x to the power m plus n plus 1 minus 1 plus x to the power m. Now you tell me. Now it's very simple. Now it's super simple. What is the coefficient of x to the power r in this expansion? Obviously, it's m plus n plus 1 CR. And over here, it will be mc. This is r plus 1. Not r, this is r plus 1. So my answer will be r plus 1 here and r plus 1 here. Making sense? Making sense? Coefficient of x to the power r plus 1 in this expansion is this, and in this expansion is this. So my final answer comes out to be m plus n CR plus 1 minus mcr plus 1. But again, needless to say, this is something which is very but obvious, that your mcr plus 1 quantity is valid if and only if your r plus 1 is less than equal to m. If and only if your r plus 1 is less than equal to m. If your r plus 1 is greater than, m, then this mcr plus 1 happens to be invalid. It is 0. It's actually contributing nothing in my answer. And in that case, my answer is very simple. M plus n plus 1, CR plus 1. M plus n plus 1, CR plus 1. Is that cool? Is that cool? Yes? So how you can remember it is, your lower indices are constant and upper indices are increasing by 1. MCR, M plus 1 CR, M plus 2 CR, M plus 3 CR, and so on, M plus n CR. So whatever is the highest upper index, highest lower index where your series is stopping, what is my answer? Plus 1 above, plus 1 below. M plus n plus 1, CR plus 1. That's majorly your answer, and the subtracted quantity arises only when the condition is met, otherwise majorly it's 0. Alright, cool, easy peasy now. Easy peasy, did you understand? Everybody? Now there's another way to prove the same result, okay? Another way. So this was your method 1. This is very interesting. This is method 1 I'll quickly share with you method 2 as well. It's very nice, and I feel many students use method 2 to prove the same result. So listen to me carefully. Very interesting, and I think you will understand it even in an easier way. This is MCR plus M plus 1 CR plus M plus 2 CR plus and so on M plus N CR. I am talking about the result which is what? NCR plus NCR minus 1 is N plus 1 CR. How many of you all know this result? How many of you all know this result? Raise your hand. By a raise of hand, please show me how many of you all remember this result. I can also write it as NCR plus 1 plus NCR is equal to N plus 1 CR plus 1. It's the same thing. I've just replaced R with R plus 1. I've just replaced R with R plus 1. Tell me, you remember this result? Yes, I'll be using the same result. So what I'll do is, I'll play smart. I will write this series ulta in the reverse fashion. It is M plus N CR plus M plus N minus 1 CR plus and so on M plus 2 CR plus M plus 1 CR plus MCR. Now what you do is MCR you already have written. MCR is written here. What if I add MCR plus 1 and subtract MCR plus 1? I have added MCR plus 1, subtracted MCR plus 1. Why? Because now what I'm going to do is, see, MCR plus 1 will give me what? M plus 1 CR plus 1. Yes or no? Yes or no? Now, M plus 1 CR plus M plus 1 CR plus 1 will give me M plus 2 CR plus 1. Can you see the chain? Can you see the chain? See, the chain has started. Now, M plus 2 CR, M plus 2 CR plus 1 will give me M plus 3 CR plus 1. And so on. When you reach till here, this will get combined with what? Tell me. This will get combined with what? M plus N minus 1 CR plus 1. This is what will keep happening. When they both combine, you will get M plus N CR plus 1. And this last quantity gets combined with the very first quantity here, and eventually you will get M plus N plus 1 CR plus 1. Bingo, guys. The chain has ended. The chain has ended. Your answer is M plus N plus 1 CR plus 1 minus MCR plus 1. This quantity, don't forget. To balance out, we had added and subtracted. With the added one, we have proceeded along with the chain, but that subtracted quantity is still left. So eventually your answer has come out to be M plus N plus 1 CR plus 1 minus MCR plus 1, which is exactly the conclusion you were getting before. Okay. So, oh, you've mastered binomial? Then am I visible, audible? People, quickly tell me. Am I visible? Am I audible? Quickly tell me. Yes? Scene is clear? Alrighty. Alrighty. Let's go then. Let's go to the question. So this question is something that I want you to master. Okay, this question is something that I want you to master. Now tell me, how exactly will you crack it? Look here, it's again a series. It's a binomial series. The question is asking you to crack the question. So let's start. Here it says summation 50 minus R C6. If you open this up, what do you get? Just try to expand and see what this is looking like. So this is looking like 50 C6 plus 50 minus 1. So 49 C6 plus 48 C6 plus 47 C6 plus and so on. Towards the end, you will get 30 C6, right? This is how your series will open and look like. Now, one thing which you can very easily observe, lower indices are throughout constant. It is equal to 6. And upper indices are increasing or decreasing by 1. See 50, then 49, then 48, then 47 and so on till 30. This is a clear signal that we are talking about type 1 series, guys. clear signal that we're talking about type 1 series. So please make sure that you understand that here I have identified the type 1 series will be applied, the result will be applied, the same algorithm will be applied. So what I'm going to do is 30C6 plus 31C6 plus and so on, 47C6, 48C6, 49C6 and 50C6. You know, this is the largest. This is the largest, right? With the largest upper index and largest lower index. So technically our answer came out to be what? It came out to be what? 50 plus 1 C6 plus 1 minus MCR plus 1. Remember, M means 30. Remember, 30 MCR, M plus 1 CR, M plus 2 CR. So MCR plus 1. Yes or no? Yes or no? 6 plus 1. That's it. So technically our answer should come out to be 51C7 minus 30C7. Tell me, is this cool? So this is from the direct result. This is your largest binomial coefficient. When I say largest binomial coefficient, I mean largest upper index and largest lower index. Now, when you directly applied the result of M plus N plus 1 CR plus 1 minus MCR plus 1, when you wrote MCR plus 1, which is 30C7, you found out it's a valid quantity because 7 is less than 30. So 30C7 is well defined. If 7 would have been greater than 30, this entire quantity would have come out to be 0 and my answer would have been just 51C7. But this is right now my answer. This is my answer. And if you want to ideally find out how did we reach to this answer, you can very easily go ahead and prove it. Very easily you can go ahead and prove it, guys. Give me 1 second. Yep. Very easily you can go ahead and prove it. How? 50C6 or 30C6, 31C6, 32C6 and so on. You want coefficient of, very simple, of x to the power 6 in the expansion of 1 plus x to the power 30 plus 1 plus x to the power 31 plus and so on 1 plus x to the power 50. Now from here to here is nothing again but a GP of 21 terms. Yes or no? And how do you resolve this? First term, common ratio to the power number of terms minus 1 upon common ratio minus 1. So 1 plus x minus 1 will just give you x. Okay, we're just trying to prove the same algorithm we applied to prove the generic result. We are applying it here in the question as well. That's why it was important for you to know the proof. Because the proof is actually a way to solve the questions. It is not just confined to proving a result. No, it's not that theoretical. That same theoretical proof is actually a proper legit solution to questions like these. Alright? Alright, making sense? If I want coefficient of x to the power 6 from here, this ideally means I want coefficient of x to the power 7 in my numerator, which is 1 plus x to the power 51 minus 1 plus x to the power 30. And that's it. What is the coefficient of x to the power 7 from here? 51C7, and from here it is 30C7, which is actually matching my answer from here. Easy peasy lemon squeezy. Is that making sense? Everybody, is that making sense? Quickly tell me, is that making sense? Yes? This is done? I hope now you have no confusion regarding the type 1, but I have another question for you. Beautiful questions for you, which is this one. Now, this is going to blow your mind away. It will literally blow your mind away. Why? It's written 51C19 plus 2 times 50C19 plus 3 times 49C19 and so on. Now, one thing is sure, if you look at the binomial coefficients, 19, 19 and so on 19. So, lower index is absolutely constant, the same throughout. But, look at upper index, 1 less and so on 1 less. Again, matching the format of type 1 series. But there is a catch. There is a slight twist here. It's 1 times 51C19, then there is 2 times 50C19, there is 3 times 49C19 and so on. There were no scalar multiples in our original type 1 series. But here there are scalar multiples, 1 times, 2 times, 3 times, 4 times and so on till 33 times. What do you think is the scenario, huh? Mr. Lord, you said you've mastered binomial. Tell me, What is this? If you've mastered binomial, what is this? What is this? Quickly tell me, what is this? Huh? What do you think is this? Huh? This is actually, if you realize, what is 51C19? It is coefficient of x to the power 19 in the expansion of 1 plus x to the power 51. This is done. What about 2 times 50C19? It is coefficient of x to the power 19 in the expansion of 2 times 1 plus x to the power 50. Next is 3 times 1 plus x to the power 49. And so on, 33 times 1 plus x to the power 19. This is what I want. This is what I want. Yes, this is how you have to decode that each of these terms are actually coefficient of x to the power 19 in the respective expansions which I've written. And the problem here is there is a 2 multiplied, there is a 3 multiplied, 4 multiplied and so on 33 multiplied, which was not the case previously in our original setup of type 1. So here is a slight modification, slight tweak. How do you think you will tackle? What is this? Anybody? What is this? Come on, anybody? What is this? This is actually an AGP. Can you see? The 1 plus x to the power 51, 1 plus x to the power 50 and so on, this is forming a GP, and 1, 2, 3, 4, 5, 6 is forming an AP. This is an AGP, people. It's an AGP of how many terms? How many terms? Quickly tell me. Do we need the number of terms? We don't need the number of terms because we have a proper hack and algorithm to solve an AGP. So I want coefficient of x to the power 19 from this entire AGP. I will consider this AGP as my S. What will I have? I will have 1 plus x to the power 51 plus 2 times 1 plus x to the power 50 plus and so on 33 times, or rather let me write a few terms just for your reference. 1 plus x to the power 49 plus and so on 32 times 1 plus x to the power 20 plus 33 times 1 plus x to the power 19. Okay. Now what is the common ratio? It is 1 upon 1 plus x. Yes or no? Common ratio is 1 upon 1 plus x. So I will multiply by the common ratio throughout. Yes or no? I will get s upon 1 plus x is equal to, I will get 1 plus x to the power 50. Here I'll get 2 times 1 plus x to the power 49 plus and so on. I will get 31 times 1 plus x to the power 20, 32 times 1 plus x to the power 19 plus 33 times 1 plus x to the power 18. Yes, easy peasy. I'm using my classic approach to solve an AGP. Nothing more, nothing less. Subtract, 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 subtract. I get s common, 1 minus 1 upon 1 plus x. So 1 plus x minus 1 gives you x, x upon x plus 1. Now this comes down as it is, 1 plus x to the power 51. Next, 1 plus x to the power 50. Can you see we've gotten rid of the scalar multiples? That's the magic. 1 plus x to the power 49 and so on. 1 plus x to the power 20. 1 plus x to the power 19 and minus 33 times 1 plus x to the power 18. Can you see this, people? Can you see this? Is this series completely visible to you? Are you able to understand what did I do? Yes, cool. Now listen to me. Now listen to me. We have sx upon 1 plus x, right? What you do is you multiply this 1 plus x to each term on the right hand side. So what will you get? You will get on the right hand side, when you multiply this 1 plus x, you will get 1 plus x to the power 52, then 1 plus x to the power 51, then 1 plus x to the power 50 and so on. Towards the end, you will get 1 plus x to the power 20 and minus 33 times 1 plus x to the power 19. That's it. Cool. Is this cool? Is this cool? Now from here to here is a very much well-defined, beautiful looking GP, people. That's how from AGP we have reduced our argument and made our life simpler by getting involved in GP. So here, what do I have? Quickly tell me. Quickly tell me. 52 minus 20 is 32 plus 1, 33. So this is GP of 33 terms. Now I'm going to play smart. If I consider GP in this same order, my common ratio will come out to be 1 upon 1 plus x. I don't want 1 upon 1 plus x. I want 1 plus x. So I will consider this GP from here to here. Okay, I will consider the GP from here to here. What do I mean? My GP will look like 1 plus x to the power 20, then 1 plus x to the power 21, and so on till 1 plus x to the power 52. I have written it in the reverse format so that now my common ratio, you can see second term upon first term comes out to be 1 plus x, not 1 upon 1 plus x. Right? All of this minus 33 times 1 plus x to the power 19. This is equal to Sx. Okay. As I said, this is GP of 33 terms, people. How do you write the sum? A common ratio to the power number of terms minus 1 upon common ratio minus 1 minus 33 times 1 plus x to the power 19. Take out the LCM, x gets multiplied here. And this is what you get. S into x, you get x squared. This is your S. This is your S, and from S, look here, I wanted coefficient of x to the power 19 in S. This is my S. If I want coefficient of x to the power 19 from here, I have x square sitting in the denominator. Equivalently, I can say I want coefficient of x to the power 21 from the numerator. Because x square is sitting niche na, in the denominator. So, upar if I'll get x to the power 21, cancel out, I get x to the power 19. So to get x to the power 19, I want coefficient of x to the power 21 from this numerator expression. Okay, I want coefficient of x to the power 21 in my numerator expression, which is 1 plus x to the power 53. Okay, minus 1 plus x to the power 20. And then minus 33 times x into 1 plus x to the power 19. Is this clear? Is this clear? Clear till here? What is the coefficient of x to the power 21 here? It is 53C21. What about here? Here any general term will look like 20CR x to the power r, where r is ranging from 0 to 20. You can never have x to the power 21 in this expansion. No term from here. Next, what about general term here? Here general term will look like 33 times 19CR x to the power r plus 1. Because there is an extra x here, no? So r plus 1, where r is again ranging from 0 to 19. So at max, the power of x can go till 20, 19 plus 1, but never 21. So you will not get any relevant term from here as well. Your answer is just 53C21, which is same as 53C32. Okay? Got it? This is the value of your left hand side expression, which is given to you as k times 52C31. It's given to you. It's given to you in the question that this is equal to k times 52C31. So tell me, 53C21 is equal to k times 52C31. This is my k. Can you compute this now? Can you compute this? 53C21 upon 52C31. This is my k. So this will be 53 factorial upon 21 factorial into 32 factorial multiplied with, here you get 52 factorial, 31 factorial, and here you get into 21 factorial. Perfect. So this and this gets cancelled out. 53 into 52 factorial, this gets cancelled out. 32 into 31 factorial, this gets cancelled out. You are left with 53 upon 32. Tell me, 53 upon 32. So 32k is actually 53. So 64 means into 2. So 64k is equal to 53 into 2, 106. That's your answer. That's your answer. Is this clear? So questions like these actually scare students a lot. These are the questions where students slip and they lose marks. And these are the questions where I don't want my students to slip and lose marks. Is this clear? So any such question comes where your lower indices are constant, upper indices are decreasing or increasing by 1, you have to remember the type 1 series. It should clearly knock the doors of your memory loudly. Knock, 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 knock. It should knock the doors of your memory loudly. Whenever you see the lower indices in the series constant and the upper indices are getting reduced by 1 each or getting increased by 1 each, please remember the type 1 series. The type 1 series should come running to you, to your memory. It should knock the doors of your memory. It should strike you. And then you know what is the procedure, what is the algorithm. I've discussed with you in detail, carefully, slowly, and very smoothly. So now, without any further delay, let's go to the next one. What is it? Yup, this is a JEE Advanced PYQ which actually came from the type 1 series. Very beautiful question. This question can be solved using that result which is NCR plus NCR minus 1 is N plus 1 CR. But that is something which kind of confuses students. Why? Because what is the quantity you need to add, you need to subtract in order to reach the answer? That is something where students generally get confused, get puzzled. So what instead we're going to do is we're going to identify if this falls in the type 1 series, we will use our algorithm to reach the answer. We will clearly use our algorithm and reach the answer. Is that making sense, everyone? Is that making sense? Quickly tell me. Is this clear? Anyone, any confusion, any doubt? Yes? So let's start. Let m be the smallest positive integer such that coefficient of x square in this expansion is this for some positive integer n. What is the value of n? What is the value of n? Tell me. Now I told you there are two ways to go about this question. See, if I start, this is method 1. Many times students go with method 1. What is the method 1? You have the expansion 1 plus x whole square plus 1 plus x whole cube plus and so on 1 plus x to the power 49 plus 1 plus mx to the power 50. Now, listen to me carefully. You want coefficient of x square from each of these expansions, right? So, coefficient of x square from here will look like 2c2. Coefficient of x square from here will look like 3c2, then 4c2, then 49c2, and from here it will look like 50c2 m square. This m square term will be extra. Mind it, m square term will be extra because it's not 1 plus x to the power 50, it's 1 plus mx to the power 50. Okay, so if you want to in detail understand, the general term here will look like 50cr mx to the power r. So if you want x square, the coefficient will be 50c2 into m square. Is this clear? That's the logic. Now, listen to me carefully. From here to here, we have to solve using the fact that NCR plus NCR minus 1 is N plus 1 CR. This is the result. My challenge is for you to use and solve this part. Now it's very simple. The only trick is write 2C2 as 3C3. 2C2 is 1, 3C3 is also 1. So instead of 2C2, write 3C3. What will you get? You will end up getting 3C3 plus 3C2 plus 4C2 plus 5C2 plus and so on 48C2, 49C2 plus this 50C2 m square that we are not concerned with. Now 3C3 plus 3C2 will give me 4C3. 4C3 and 4C2 will give me 5C3. 5C3 and 5C2 will give me 6C3. Yes or no? And so on. Next, combined with 48C2 will give me 49C3. Next, this and this will give me 50C3. So I will eventually get 50C3 plus 50C2 m square. Yes or no? 50C3 plus 50C2 m square. This is what I will get. I have done nothing. I have done nothing. I've just used my result. Which one? NCR plus NCR minus 1 is N plus 1 CR. This is the result which I have constantly used again and again and again and again and again, multiple times to get my answer. Is this cool? This value is given to you in the question to be 3n plus 1 times 51C3. 3n plus 1 times 51C3. Now let's simplify, okay? Let's simplify. 50 factorial upon 3 factorial into 47 factorial into 50 factorial upon 2 factorial into 48 factorial m square is equal to 3n plus 1 as it is 51 factorial upon 3 factorial into 48 factorial. Cool. Okay, this is 51 into 50 factorial. So this gets cancelled out. 48 into 47 factorial, again 48 into 47 factorial, this gets cancelled out. Is this cool? Yes or no? Is this cool? Yes. Now this is 3 factorial. This is 3 into 2 factorial. This is 2 factorial. Again, this is 3 into 2 factorial. 2 factorial, 2 factorial, 2 factorial cancels out. So you are left with m square upon 3 times 48 is equal to 3n plus 1 into 51 upon 3 into 48. Oh, this is not into, this is plus. Plus, 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 plus. So you have 1 upon 3 plus m square upon 48 is equal to 3n plus 1 into 51 upon 3 into 48. Tell me. Tell me, is there any problem? Any problem, any confusion? 50 factorial. If you want to write it again, you can write it again. Write it again and solve in detail. Please write it again and solve in detail. There are cancellations happening. Hi Ayush, there are cancellations happening. What are you getting? If you want, you can bring everything to the left hand side and then go to the right hand side. If you want, you can bring everything to the left hand side and then whatever is left, take it to the right. 3n plus 1, keep it to the right, rest everything bring to the left. Tell me, have you solved this? It's just basic arithmetic, basic. Quick. Tell me, what I'm trying to say is, you can write it as 50c3 plus 50c2 m square whole upon 51c3. This is equal to 3n plus 1. This is what I'm saying. This is what I'm saying. So basically, you will write it as 50c3 upon 51c3 plus 50c2 upon 51c3 m square is equal to 3n plus 1. This is what I am saying. And now very carefully you break it up. 50 factorial upon 3 factorial into 50 minus 3, which is 47 factorial, multiplied with 51 factorial into 3 factorial into 48 factorial. This is one bracket. Plus, be very careful, 50 factorial upon 2 factorial into 48 factorial, and this is along with m square, multiplied with upon 51 factorial, then 3 factorial, and then 48 factorial. Is this cool? Is this cool? This is equal to 3n plus 1. Perfecto. Now you know what's the scene. 3 factorial cancels out. Here is 51 factorial. You can write it as 51 into 50 factorial. So this gets cancelled out. 48 factorial is 48 into 47 factorial. This gets cancelled out. And now you are just left with what? 48 upon 51. Which is what? 3 into 1, 3 into 6, 3 into 17. So 16 by 17. Come to the next bracket. Come to the next bracket again. This is 51 into 50 factorial. This gets cancelled out. 3 into 2 factorial. So 2 factorial cancels out. 48 factorial cancels out. All you are left with is 3 upon 51, which is 1 upon 17. So you are left with 16 upon 17 plus m square upon 17 is equal to 3n plus 1. Or rather, I can say this is 16 plus m square is equals to 91n plus 17. So m square is equal to 91n plus 1. 51, not 91, 51. That means if you want smallest value of n, for which 51 n plus 1 is an integer, you actually want the smallest value of n corresponding to which you get m square, or rather a perfect square as the answer. What is that smallest value of n for which 51n plus 1 gives you a perfect square as the answer? If you plug in n as 1, not a perfect square. N as 2, not a perfect square. N as 3, 4, 5, not a perfect square. Is 5 working? Is 5 working? Tell me quickly. Is 5 working or 6 working? If you plug in n as 5, you will get 255 plus 1 will give you 256. So for n equals 5, your m square is coming out to be 256, which is, yes, a perfect square. This implies m is 16. So your n is 5, m is 16. The least value of n for which this relationship is getting satisfied, the integral value, positive integral value, is 5. So n is 5. Did you understand? The answer to this is 5 very clearly. But I have reached to this answer by using my result NCR plus NCR minus 1 is n plus 1 CR. Again and again and again and again, I reached to 50C3, then I added it with 50C2m square, and after that it was just arithmetic solving. But method 2, guys, method 2, very important for you to know, very, very important. You had 1 plus x whole square, then 1 plus x whole cube, plus and so on. Then you had 1 plus x to the power 49, and then 1 plus mx to the power 50. Yes or no? Let me check. Yes. You wanted coefficient of x square in this expansion. Getting my point? What do you want? You want coefficient of x square. Let me write coefficient of x square in this expansion. This is your method 2. In this expansion, people. Now, coefficient of x square from here I know is 50c2m square. But what about till here? Batao, tell me. What about till here? 1 plus x whole square, 1 plus x whole cube and so on, 1 plus x to the power 49. This is a GP now, people. This is GP of 48 terms. 49 minus 2, 47 plus 1, 48. Yes or no? Common ratio is 1 plus x. So you are getting a common ratio to the power number of terms minus 1 upon common ratio minus 1. So if you want coefficient of x square in this entire expansion, and don't forget there is a plus 50c2m square being carried forward as it is. If you want coefficient of x square from here, there is an x sitting niche, no? So you equivalently want coefficient of x cube from the numerator, which is 1 plus x to the power 50 minus 1 plus x whole square. From here you want coefficient of x cube, and in that you will add 50c2m square. Tell me what is the answer from here? Your answer is 50c3. And here do you get any term with x cube in it? No, you will not. So you just have 50c3 plus 50c2m square. What is it? 50c3 plus 50c2m square. This is exactly what you were getting from here. 50c3 plus 50c2m square. Can you see this? Look above. 50c3 plus 50c2m square from method 1, 50c3 plus 50c2m square from method 2. Once you have this with you, equate it with the quantity given in the question, and then there is, as usual, arithmetic solving. You have to find the smallest value of n for which m square comes. That means for which your 51n plus 1 is a perfect square. That will give you the value of m as well. Okay? Is this cool? So this is how your type 1 series actually works out. We've spent a lot of time on type 1 because this is the only complicated one. This is the only complicated series. Otherwise, the remaining series are really very easy to tackle. For example, look here, type 2. Look here. Type 2 says summation R n C R. So simple, R going from 1 to n. Now, it's very simple, very important, supremely repeated series in the questions of JEE Main. Supremely repeated. What is this equal to? This is summation R. NCR you know is n upon R, n minus 1 CR minus 1. Remember this property? Remember or not? NCR is nothing but n upon R, 1 n, 1 R gone. So you're left with 1 less n, 1 less R. This is the property I've used here. R cancels out, n is a constant, comes out of the summation. So you get n times summation n minus 1 c r minus 1, r going from 1 to n. Now when you will open this up, listen to me carefully. When you open the summation up, you end up getting n multiplied with n minus 1 c0 plus n minus 1 c1 plus n minus 1 c2 plus and so on n minus 1 c n minus 1. And what is this, folks? What is this? Come on. What is this? Anybody, any clue? What is this? Huh? Anybody, any clue? Wild guess. Wild guess. Give me wild guess. I don't want it to be super wild. I actually want it to be correct. So NC0 plus NC1 and so on till n minus 1 Cn minus is nothing but sum of all binomial coefficients in the expansion of 1 plus x to the power n minus 1, which is 2 to the power n minus 1. So your answer is n into 2 to the power n minus 1. Guys, please remember summation r NCR is nothing but n into 2 to the power n minus 1. Everybody remember right now, summation r NCR is n into 2 to the power n minus 1. What about type 3? I'll share with you type 3. Wait a second. Yes. What is type 3? It says summation r square NCR, r going from 1 to n. Again, simple approach, same approach. I want to get rid of something which is varying. R is varying, I want to get rid of r or r square. That's my very first scenario. Like in the previous result, type 2 as well, what did I do? I got rid of r. How? By writing NCR as n upon r n minus 1 CR minus 1 so that these r's get cancelled out and I don't have any more r in picture. Cool. Here I have r square in picture. So I want to get rid of this variable part which is r square. How exactly do I proceed? Carefully listen to me. I write it as r into NCR. Now look at the steps, okay? Very intelligently I'm going to perform the steps. This is n upon r n minus 1 CR minus 1 r cancels out. Now 1 n I have obtained which is a constant. It will jump out of the summation sign. I will get n then summation r into n minus 1 CR minus 1. Correct till here? Easy peasy lemon squeezy. Now I'm going to play smart. This r I will manipulate. I will write as r minus 1 plus 1. I will write it as r minus 1 and plus 1 and n minus 1 CR minus 1 as it is. Now I will be distributing r minus 1 along with this, 1 along with this. So in the next step I get n as it is summation r minus 1 n minus 1 CR minus 1 plus summation n minus 1 CR minus 1, r going from 1 to n, r going from 1 to n. Now see how intelligent this is. When I talk about this part, what is this? N minus 1 C0 plus n minus 1 C1 plus and so on n minus 1 Cn minus 1. This is nothing but 2 to the power n minus 1. No, I just now told you. This is representing sum of all binomial coefficients in the expansion of 1 plus x to the power n minus 1. So the answer is 2 to the power n minus 1. Perfect. This summation is solved. What about this summation, Baba? What about this summation? Again, same approach, guys. Same approach. You have r minus 1 written. N minus 1 CR minus 1. Break it down further. You will have n minus 1 upon r minus 1. 1 less upar. N minus 2. C 1 less niche r minus 2. So r minus 1 cancels out. N minus 1 is a constant. It will go out of the summation. You are left with summation n minus 2 C r minus 2. R going from not 1 to n. Now you will have to write 2 to n. Because if you plug in r as 1, you will get n minus 2 C minus 1. That doesn't make sense. We are dealing with whole numbers whenever we write NCR. N is a natural number, r is a whole number. The lower index cannot be minus 1. Okay, so I will start it from r equals 2, not r equals 1. And when I do that, what do I end up getting? N minus 1 to chalo as it is. Then I have what? N minus 2 C0 plus n minus 2 C1 plus and so on n minus 2 C n minus 2. And this series is nothing but 2 to the power n minus 2. Yes or no? The series is nothing but 2 to the power n minus 2. Do you see this? This series? This series that I have written, can you see this? This is 2 to the power n minus 2. Yes or no? Sum of all binomial coefficients sitting in the expansion of 1 plus x to the power n minus 2. Bingo people, all the summations are solved. Now just write it down neatly. This n remains here, so I'm going to write n as it is. Bracket start. Inside what do you have? n minus 1 into 2 to the power n minus 2, alrighty, n minus 1 into 2 to the power n minus 2. After that you have plus 2 to the power n minus 1. Remember, plus 2 to the power n minus 1. Perfecto. Perfecto. What next? Tell me what next? Huh? What next? See, n into 2 to the power n minus 2 comes out common. You're left with n minus 1 plus 2. Yes or no? So you will get n. This is n minus 1 or n plus 1? N minus 1. Yes, n minus 1. 2 to the power n minus. Okay, plus 2. Na? So this is n plus 1. Yes or no? N minus 1 plus 2 gives you n plus 1, n plus 1, 2 to the power n minus 2. Is this cool? Is this clear? So again, please remember, summation r square NCR, r running from 1 to n is equal to n plus 1, 2 to the power n minus 2. Cool? Cool? This is type 3. So 3 results we are down with. What about type 4? Very interesting. Summation NCR upon R plus 1, R going from 0 to n. What is this equal to? Very simple proof, Baba. Very simple proof. What is the proof? Absolutely simple proof. See, NCR is equal to n upon R, n minus 1 CR minus 1. I just told you. Now, instead of n, write n plus 1. Instead of R, write R plus 1. You will get n plus 1 upon R plus 1 into NCR. Yes, that means NCR upon R plus 1 I can write as n plus 1 CR plus 1 upon n plus 1. This trail should be understood by you. You have to absorb it. You have to make it get internalized in your system. Absorb it, digest it, completely accept it, make it your part. NCR upon R plus 1 is written in my question. I will replace it directly with n plus 1 CR plus 1 upon n plus 1. This itself is equal to n plus 1 CR plus 1 upon n plus 1, R going from 0 to n. So 1 upon n plus 1 is constant. No, it will come out. Inside you're left with n plus 1 CR plus 1, R going from 1 to n. But here's a catch. Here's a catch. Here is a slippery area where a lot of students commit mistake. 1 upon n plus 1 as it is. Inside, what is the expansion? Write it down precisely. You will get n plus 1 C1 plus n plus 1 C2 plus n plus 1 C3 and so on, n plus 1 C n plus 1. What is missing? What is missing? N plus 1 C0 is missing. Yes or no? You add n plus 1 C0. You subtract n plus 1 C0. So what about from here till here? This is completely 2 to the power n plus 1. And what is this? This is 1. So your answer comes out to be 2 to the power n plus 1 minus 1 upon n plus 1. Please remember this. Summation NCR upon R plus 1 is 2 to the power n plus 1 minus 1 upon n plus 1. Extremely important. We are down with 4 types. Just left with 3 more. I have right in the beginning told you there are 7 powerful results. We're just left with 3 more. Okay? But before I move any further, let's attack this question. Tell me. Tell me quickly tell me. What will you do in this question? What will you do in this question? Some of the series, it's just asking some of the series. I told you whenever there are series involved, whenever there are questions on series involved, you have to use your results on binomial series. We are down with type 1, down with type 2, down with type 3, down with type 4. Yes or no? MCR plus M plus 1 CR plus M plus 2 CR and so on till M plus NCR. Next was summation R NCR. Next was summation R square NCR. Next was summation NCR upon R plus 1. We're down with 4 different types of series and then this question is popping up. That obviously means somehow it's connected with the previous 4 types. So what is it reminding you of? What is it reminding you of? Tell me quickly. Tell me. What is it reminding you of? Come on. Can you decode the pattern? Look, it's 20C0, 20C1, 20C2, 20C3, 20C20. So obviously it's 20CR, summation 20CR, R running from 0 to 20. But there are scalar multiples involved. No, there is a 2, there is a 5, there is an 8, there is an 11 and so on 62. So something has to be multiplied to this 20CR to give me a general term of this entire series. And what is that something sitting in the bracket which I still don't know? What is that something? It's actually the general term corresponding to the sequence 2, 5, 8, 11 and so on. And guys, this is an AP. Very good, Naresh. Very, very good. This is an AP, people. This is an AP. You want to know what is the general nth term or the rth term. It will look like A plus R minus 1 times the common difference. So 2 plus 3R minus 3. This will give you 3R minus 1. This is a general term. Can you write it here? Can you write this one here? You can't. Because now this is your general term. Please check. Please always check. Is it actually giving you the original terms in the series or not? When you plug in R as 0, the first term you get is 20C0 into minus 1, which is not matching my first term. So this is not the general term of my bracketed expression. What I'm going to instead do is I will take the next term after 3R minus 1. It's an AP. If 3R minus 1 doesn't work, the next term sitting in the same arithmetic progression will be 3R minus 1 plus the common difference. So 3R minus 1 plus the common difference will give me 3R plus 2. If this also doesn't work, I will take even the next term or the terms before. Anything might work. If 3R minus 1 doesn't work, I will take the term sitting next to it or take the term sitting before it. I have to check. This is something which I have to check. Here, if I plug in R as 0, I will get 20C0 into 2, which is matching my first term. If I plug in R as 1, I will get 20C1 into 5, which is matching my second term. Bingo, people. It's working. This is working. This is perfect. 3R minus 1 did not work. 3R plus 2 is working. Absolutely correct. Awesome job done. And now what will you do? Very simple. Just distribute summation 3R into 20CR plus 2 times summation 20CR. This 3 comes out. It's a constant. R going from 0 to 20. R going from 0 to 20. Now here there is no sense of R going from 0 to 20 because 0 into anything will give you 0. So you can very comfortably start your summation with 1. Okay. Summation R NCR is n into 2 to the power n minus 1. N into 2 to the power n minus 1 plus 2 times summation NCR. R going from 0 to n is 2 to the power n. Yes or no? Easy peasy lemon squeezy. You are getting 3 into 10 into 2 to the power 20 plus 2 to the power 21. This is what? 2 into 5? No. 2 into 10. Yes, 6. 6 into 10 into 2 to the power 19 plus 2 to the power 21. Tell me. Quickly, quickly, quickly. Quickly, tell me quickly, quickly, quickly. What is the answer? Huh? By 2 to the power 20, so you can write na. Let this be 5 and make this 2 to the power, or rather, write it like this. Okay. 2 to the power 20 is here. You can write this 20 as 10 into 2. So you basically get 30 into 2 to the power 20 plus 2 into 2 to the power 20. So 2 to the power 20 comes out common. You're left with 32. 32 is 2 to the power 5. So your answer is 2 to the power 25. Is this question absolutely clear? Is this hashtag HDCC? Is this question hashtag HDCC? Yes or no? Please tell me quickly. Is this question completely clear to you? Yes, ma'am. No, ma'am. Yes, ma'am. No, ma'am. Cool? Absolutely correct. Then let's move ahead. Go to this question. This is a JEE Advanced PYQ. Quickly tell me, how will you solve this? You want the determinant of this 2 cross 2 matrix. You want the determinant of this 2 cross 2 matrix. And that determinant you have to equate with 0. You're given a matrix, a 2 cross 2 matrix, but you actually want to compute the determinant. Okay? And then once you have the value of n with you, then compute summation nck upon k plus 1, k going from 0 to n. Beautiful question. This question has all the series that we have done till now. Everything involved. Everything involved. What do you think? What do you think? This is summation k going from 0 to n. I'm computing the determinant. This is summation k square into nck, k going from 0 to n. Next is summation k times nck, k going from 0 to n. And next is summation nck 3 to the power k, k going from 0 to n. This determinant is what you have to compute and equate with 0. This determinant is what you have to compute and equate with 0. What will you do? You know, determinant of a 2 cross 2 matrix is product of diagonal minus product of off diagonal. Product of diagonal minus product of off diagonal. But first of all, let's write the values, no? What are the values of these quantities, these series? Huh? What is summation k? What is summation k? K going from 0 to n. It's like 1 plus 2 plus 3 and so on plus n. Sum of first n natural numbers, which we all know is n plus 1 by 2. What about this? Summation k square nck, k going from 0 to n. Write it 0 to n or 1 to n, it's the same thing. Because the first term corresponding to k equal to 0 will be 0 only. It will not contribute anything to my answer of the series. Summation r square ncr is n plus 1 2 to the power n minus 2. n plus 1 2 to the power n minus 2 we just learnt. Type 3 series. What about this? Summation r ncr, which is n into 2 to the power n minus 1. Bingo. What about this series? What about the fourth series? I've told you right in the first lecture of binomial. How do you rewrite this? How do you interpret this? You write it as summation nck 1 to the power n minus k 3 to the power k, which is nothing but 1 plus 3 to the power k, which is 1 plus 3 to the power n, which is 4 to the power n. Yes or no? So all the 4 quantities we have decoded successfully. All the 4 quantities are nothing but the sum of binomial series. And we are well versed with them. So the moment we decode, the terms appear which are there in the determinant. And now product of diagonal minus product of off diagonal equal to 0 is what we have to do. Product of diagonal will give you what? This into this. So 4 to the power n into n plus 1 upon 2. Product of diagonal minus product of off diagonal will be this into this. So n into 2 to the power n minus 1 multiplied with n plus 1 2 to the power n minus 2. Perfect. This is equal to 0. So when this minus this is 0, it's equivalent to saying that this is equal to this. Right? You take one term to the right hand side. No, they both are equal. Now n plus 1 cancels out. 2 to the power, this is what? 4 to the power n is 2 to the power 2n. So you get 2 to the power 2n minus 1 equal to n into 2 to the power n minus 1 into 2 to the power n minus 2. So you have 2 to the power 2n minus 1 minus n plus 1 minus n plus 2. Okay, so 2n minus n minus n 0, minus 1 plus 1 cancels out. You are left with n equal to 2 square, which is 4. Bingo guys, this question is done and dusted. Done and dusted. Done and dusted. Gone, shot, conquered, killed, smashed. Completely. It's gone. Bye-bye. The moment you see it, it looks pretty scary. But the moment you start solving and you realize that the 4 terms sitting in my matrix are nothing but sum of my series, actual results. The moment you recall them, The only game is about recollecting. The moment you recall, plug in the values, simplify the determinant, which you already know, product of diagonals minus product of off diagonals equal to 0. Simplify this, n comes out to be equal to 4 very easily. The moment n has come out to be equal to 4, now you want to compute summation k going from 0 to 4, 4ck upon k plus 1. Come on, tell me what is this? Summation ncr upon r plus 1, r going from 1 to n. Write it from 0 to n or 1 to n. Oh, 0 to n. Yeah, 0 to n. This is equal to 2 to the power n plus 1 minus 1 upon n plus 1. So 2 to the power n plus 1 minus 1 upon n plus 1. This is your answer. Baba, is this making sense? Please tell me quickly. Did you understand? Is this question completely clear to you? What did I do? This question is actually a check whether you remember all your type series or not. Type 1, type 2, type 3, type 4, even the actual binomial expansion got tested here. Summation nck 3 to the power k. This is nothing but 1 plus 3 whole to the power n, which is 4 to the power n. Something you must remember. At the drop of a hat, you should be able to tell me what is summation nck 3 to the power k. What is summation nck 2 to the power k? It is 1 plus 2 whole to the power n. What is summation nck 5 to the power k? It is 1 plus 5 whole to the power n. What is summation nck minus 1 to the power k 2 to the power k? It is 1 minus 2 whole to the power n. Yes or no? Everything should be on your fingertips. All these series, their results, their conclusions, their answers, their values should be on your fingertips. Cool? Are you ready for the next type? 5, 6, 7. 3 more types to go. Are you ready for the next type? Are you ready for the next type? This is type 5, people. Please make sure you listen to me very carefully. This is again extremely important. Highly repeated series in your paper in the last 5 to 6 years. The weightage of this series, which I'm about to reveal, is supremely huge. JEE Main loves asking questions based upon this binomial series. What is it? What is it? Take 2020 or 2021, 2022, 2023, 2024. This series has been an absolute favorite of NTA. And even in 2025, this holds great deal of chance to land in the paper. It is none other than the series of product of binomial coefficients, where you check the sum of lower indices to be constant or not, and accordingly you write the answer. What is it? Summation NCR whole square. R going from 0 to n. Yep, that's it. This is the series, people. This is a series of product of binomial coefficients. When you open this up, what happens? This looks like summation NCR into NCR, R going from 0 to n. Now, the only catch here is you have to check the sum of lower indices. The sum of lower indices right now is coming out to be 2R, which is not equal to constant. To make it constant, to make the sum constant, what do? You use the property NCR equals NCR minus 1. Oh, not R minus 1, N minus R. NCR is same as NCN minus R. Accordingly, how do you manipulate your expression? It looks like summation NCR NCN minus R. Now, when you try to add the lower indices, the sum will come out to be N, which is a constant. Bingo, people. And that is when you write the final answer to be equal to what? Sum of upper indices, C, sum of lower indices. Sum of upper indices, C, sum of lower indices. This is your absolute shortcut to reach to the answer of such a series. Series of product of binomial coefficients looks like summation NCR whole square. When you break it up, it happens to be summation NCR into NCR. Sum of lower indices is 2R, not constant. To make it a constant, you use the result NCR is equal to NCN minus R in one of the binomial coefficients. When you do that, now the sum of lower indices comes out to be equal to a constant, which is N. So what is your final answer? What is your final answer accordingly? Because now the setup is summation product of binomial coefficients where the sum of lower indices is equal to constant. So your final answer, direct shortcut to write the answer is sum of upper indices, C, sum of lower indices. 2N, C, N, bingo, done and dusted. Okay, cool. Making sense? I'll repeat this one for you. Extremely important series, people. This is loved by NTA. Questions from here have been asked again and again in the last 5-6 years. And even in 2025, this result holds great deal of chance to land in the paper. This binomial series is summation NCR whole square, or rather summation of product of binomial coefficients. Whenever you get such a series, always number one, check the sum of lower indices is constant or not. If it is not a constant, what do? In one of the binomial coefficients, you rewrite it as NCR, you rewrite it as NCN minus R. Now when you add the sum of lower indices, you consider the sum of lower indices, it will come out to be a constant, and eventually your final answer will be what? Now the setup is summation, product of binomial coefficients, where the sum of lower indices is constant. So your final answer as per the direct shortcut comes out to be sum of upper indices, C sum of lower indices. Bingo, done. That's it. Okay, very important series in your pocket, just like that. Now let me show you a detailed proof of this, because you're going to enjoy it thoroughly. See, look at this, because type 1 series you've understood, no? So this one also you'll very easily understand. If I have summation NCR whole square, this is nothing but summation NCR into NCR. When you open this up, R going from 0 to N, R going from 0 to N. Please understand very carefully, this is something which will help you not slip in questions involving this series. Otherwise, this series, questions based upon this series, can actually make or break your score. There is a very slight margin, or I should say boundary, of being careful. If you become overconfident with this series, you can end up committing mistakes. So there is a boundary to which the result or the shortcut gets applied. There is a threshold. What is it? I'll just explain. When you open this up, you will get NC0, or rather, NC0 into NC0 plus NC1 into NC1 plus NC2 into NC2 plus and so on NCN into NCN. The very first thing you have to do is always catch hold of sum of lower indices. When you add the lower indices, you are not getting constant all the time. Here the sum is 0, here the sum is 2, here the sum is 4, here the sum is 2n. So to make the sum of lower indices constant, you know what to do? What to do? Replace NCR with NCN minus R. Any one binomial coefficient in each term, you replace it with its counterpart, NCN minus R. So what will you get? NC0 as it is, this will be NCN. NC1 as it is, this will be NCN minus 1. NC2 as it is, this will be NCN minus 2. Plus and so on, NCN as it is, this will be NC0. Now check. Sum of lower indices everywhere is N. Sum of lower indices is equal to constant. Bingo. My effort is not wasted, it's completely successful. But what are you getting? NC0 into NCN plus NC1 into NCN minus 1 plus NC2 into NCN minus 2 plus and so on NCN into NC0. What is this, guys? What is this? Sum of lower indices is constant. It is equal to n throughout in every term. But what is this? This is nothing but coefficient of x to the power n in the expansion of 1 plus x to the power n into 1 plus x to the power n. How many of you all are able to understand this? Because the moment you will open this expansion, what will you get? NC0 plus NC1x plus NC2x square plus and so on NCN x to the power n multiplied with the same expansion. NC0 plus NC1x plus NC2x square plus and so on NCN x to the power n. If I want coefficient of x to the power n, what all I have to multiply? NC0 into NCN, NC1 into NCN minus 1 and so on NCN into NC0. So all the possible combinations which can give me the coefficient of x to the power n are all sitting here. Each and every coefficient of x to the power n that you can possibly get is sitting above. All the terms are exhausted in the series from here to here. Got it? Yes or no? Got it? When you multiply 1 plus x to the power n with 1 plus x to the power n, all possible coefficient of x to the power n which you can get are all written in the above series. Exhausted, completed. The list is complete. So what I'm going to do is, what is coefficient of x to the power n in this expansion? This is nothing but 1 plus x to the power 2n. What is this? This is 1 plus x to the power 2n. And what is the coefficient of x to the power n in this expansion? It is 2n cn, and that's my answer. This is exactly what you are getting even when I told you the shortcut. That bache, whenever you get sum of product of binomial coefficients, whenever you get the series which is summation of product of binomial coefficients, always check the sum of lower indices. If it doesn't come out to be a constant, you take any one NCR or any one binomial coefficient and you rewrite it as NCn minus R. Now you add the sum of lower indices. If it comes out to be a constant, great. What will be your answer eventually? Sum of upper indices, C sum of lower indices. But you can't apply this shortcut blindly. You have to check two things. Number one, all the terms in the series are exhausted or not. Because this series is representing coefficient of something in the product of two expansions. If all coefficients are exhausted, then only this shortcut works. If they are not exhausted, this shortcut will not work. And second thing you have to check is that sum of lower indices is coming out to be constant or not. ठीक है? ठीक है? Cool? Making sense? Making sense? For example, if I tell you summation NCR whole square R going from 1 to n. This is what? This is what? This is again the same thing. You have the coefficients of x to the power n, but one coefficient is missing. Which one is missing? NC0 into NCn. This is missing. All are not exhausted. And that is why the answer will be 2NCn minus 1. It's like you are adding NC0 into NCn and subtracting NC0 into NCn. So when you add NC0 into NCn, the series get completed. Your answer is 2NCn. Subtract NC0 into NCn, that means subtracting 1. Got it? Please don't forget this. Please don't forget this. Very, 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 very important. Is this cool? Is this cool? Now, question arises, what if there exists alternate signs in type 5 series? Like here in the type 5 series, what was happening? What was happening? It was all throughout plus, no? It's all throughout plus. Can you see this? NC0 into NCn plus, NC1 into NCn minus 1 plus, then plus, then plus. So I have product of binomial coefficients as each term, but the terms are actually getting added only. It's throughout plus. What if there is alternate plus minus sign? What if there is alternate plus minus sign? For that, understand this question. Very, very important. Guys, understand this question very carefully. It says 30C0 into 30C10 minus 30C1 into 30C11 plus 30C2 into 30C12. Again minus, then plus, then minus, then plus, and so on. Last term is 30C20 into 30C30. Cool? Now the problem is, again, you can see this is a series. It's a binomial series which involves product of binomial coefficients as each term. The very first exercise is whether the sum of lower indices is constant or not. Right now, the sum of lower indices in each term is not the same. It's not constant. So I will make it a constant. How? By using my result NCR equals NCn minus R. So I am going to do what? 30C0 as it is. This will be 30C20 minus 30C1 as it is. This will be 30C19 plus 30C2 as it is. This will be 30C18. And so on. Eventually, I'll have 30C20 as it is, 30C0. Now again check. Sum of lower indices 20, sum 20, sum 20, sum 20. So sum of lower indices. That's the first thing to check, guys. First thing to check. Sum of lower indices is equal to 20. Bingo. Perfect. Second thing to check is whether all terms are exhausted or not. What do I mean? What do I mean by second thing to check is check whether all the terms are exhausted, or rather included or not. What does that mean? See, 30C0 into 30C20 minus 30C1 into 30C19 and so on. Sum of lower indices throughout is 20. That means this is representing coefficient of x to the power 20 in which expansion? 1 plus x to the power 30 minus 1 plus x into 1 minus x to the power 30. How? Why? How? How exactly? I'm confused. Of course, I can understand that you might be confused. You shall not be. Because, let's write this down. Open this up. We are trying to visualize things. We are trying to make all of this a part of our system because this is not a supremely easy topic, guys. But this is a topic where students slip the most. This is the topic where NTA likes to lay traps for you the most. So you have no option but to excel at it. Just master these 7 results and trust me, your life will be supremely easy. And these 4 marks which you get from here, guaranteed in your pocket, guys, guaranteed. So let's start. This is 30C0 plus 30C1x plus 30C2x square plus and so on, 30C30x to the power 30. Cool. Next is 1 minus x to the power 30. So 30C0 minus 30C1x plus 30C2x square minus and so on, 30C28 x to the power 28 minus 30C29 x to the power 29 plus 30C30 x to the power 30. Now you want coefficient of x to the power 20. What all ways you can get coefficient of x to the power 20? 30C0 into 30C20, 30C1 into 30C19, 30C2 into 30C18 and so on, 30C20 into 30C0. Each and every of these coefficients is written over here. That means all possible coefficients that you can get when you multiply both these series are already exhausted. They are included in my series. No term is left. No potential coefficient of x to the power 20 is left. No potential coefficient of x to the power 20 is left. Everything is exhausted in the series. These are my 2 conditions. These are my 2 conditions. Okay, now what happens? 1 plus x to the power 30 into 1 minus x to the power 30 gives you 1 minus x square to the power 60. And in this expansion, what is the coefficient of x to the power 20? General term looks like what? Here, the general term looks like what? It looks like 60 CR minus 1 to the power r x to the power 2r. Yes or no? General term looks like 60 CR minus 1 to the power r x to the power 2r, where your r is ranging from 0 to 60. So if you want x to the power 20, that means r you have to plug in as 10. So you will get 60 C10 minus 1 to the power 10 x to the power 20. That's it. Not 60, 30. Why did I write 60? 30, 30. 30, 30, 30. Okay. 30C10 into minus 1 to the power 10 is the coefficient of x to the power 20. So my answer is just 30C10. My answer is 30C10, which is same as 30C20. This is how beautifully these questions are done, which involve binomial series where each term is nothing but product of 2 binomial coefficients. The only 2 conditions you have to check are sum of lower indices is constant or not, and check whether each and every term is exhausted or not in the series. I am not saying blindly check that r is varying from 0 to n or not. That I am not asking you to check. R might vary from 0 to n, might not vary from 0 to n. Even if it doesn't vary from 0 to n, that does not mean that all terms are not exhausted. It might also mean that all terms are exhausted. For example, so don't blindly see summation r going from 0 to n means all the terms are exhausted. No. I'll just share with you another question like this one. Look at this question. I'll just prove this to you what I just said, because students blindly say, ma'am, whenever it's written summation r going from 0 to n and there is NCR whole square, we directly write it as 2NCN. This is not right. Remembering it like this is not right. Right now as a result, it's true. But remembering it like that is not right. Because you need to know the details, you need to know the unlayering as well. Each and every layer you should know about this. So what I actually mean is, that will be clear from this question. See, look at the two series which are being subtracted. If I look at the first series, it is what? Summation 31ck and 31ck minus 1, k going from 1 to 31. Now the problem here is, summation is varying from 1 to 31, not 0 to 31. So does that mean that all terms are not exhausted? Well, I'll show it to you. I'll prove it to you. See, if I apply the shortcut, my claim is that all terms are exhausted. My claim is all terms are exhausted. So if all terms are exhausted, my only target is sum of lower indices is constant or not. Let's check. Sum of lower indices right now is 2k minus 1. This is not equal to constant. So I will make it constant. How? Summation 31ck, and this I will replace with 31c, 31 minus k plus 1. So 32 minus k. Perfect. Now the sum is 32, which is a constant. And k is varying from 1 to n. My claim is all terms are exhausted. My claim is all terms are exhausted. Even if the summation is varying from 1 to n, not 0 to n, my claim is all terms are exhausted. Secondly, the sum of lower indices is coming out to be a constant. So I will directly apply my shortcut, which is sum of upper indices, C sum of lower indices. This is also equal to 62C 30. But how are you so sure, ma'am, all terms are exhausted? Listen to me carefully. This and this is the same. When you open this series up, what are you getting? 31C1, 31C31 plus 31C2, 31C30 plus 31C3, 31C29 plus and so on. Lastly, I have 31CN, 31C32 minus N. Correct? The sum of lower indices is 32. That means what is this representing? This is representing coefficient of x to the power 32 in what expansion? 1 plus x to the power 31 into 1 plus x to the power 31. Yes. And when you open this expansion and this expansion, and you check how, in what all manners, in what all possibilities can I get the coefficient of x to the power 32, you will realize these are the only ways. 31C1 from one expansion, 31C31 from another expansion, 31C2 from one expansion, 31C30 from another expansion, and so on and so on. Lastly, 31CN into 31C32 minus N. These are the only ways to reach coefficient of x to the power 32. 31C0 into something will not give you coefficient of x to the power 32 because there is no x to the power 32 term present in any of these expansions. So you don't need 31C0, which you are trying to find. Ma'am, there is no 31C0, one term is missing. One term is missing. No, it's not missing. So don't blindly go after summation varying from 0 to n, 0 to n, 0 to n. No. Check whether all terms are exhausted or not. Secondly, check whether the sum of lower indices is constant or not. Because here all terms are exhausted, my answer again from here also will come out to be the same. This is 1 plus x to the power 62. And here what is the coefficient of x to the power 32? It is 62C32, which is same as 62C30. It's the same. It's the same. You use the direct shortcut approach or you use the lengthy approach, it's the same. The only two conditions you need to check before you apply the shortcut is number 1, sum of lower indices is constant or not. Number 2, all terms are exhausted or not. Got my point? Is this clear? Am I making sense? Next series is what? Summation 30ck, 30ck minus 1, k going from 1 to 30. Again the same thing. The series looks like product of two binomial coefficients. Yes or no? But here again you can see the sum is 2k minus 1, which is not equal to constant. So now I will make the sum constant. How? Summation 30ck and 30c, 30 minus k plus 1, so 31 minus k. Now you can check the sum is 31, which is constant. K is not going from 0 to n, it's going from 1 to n. But again, open this up, actually you will realize when you open it up as this is an expansion, and look at the terms, you will realize that this is exhausting all possible coefficients of x to the power 31. All. You don't need k to be 0. You don't need k to be 0. K going from 1 to n is actually exhausting all possible coefficients of x to the power 31 from the expansion of 1 plus x to the power 30 into 1 plus x to the power 30, which is 1 plus x to the power 60. Okay, so from here, you can directly apply the shortcut, sum of upper indices, C sum of lower indices. Is this cool? Is this cool? This is also equal to 60C 29. Okay guys, got it? So both these series are solved. 62C30, this is 62C30 minus 60C29, this is equal to alpha times 60 upon 30 factorial into 31 factorial. Now this is something you can very easily solve and get to the value of alpha, which is very simple task. Okay, just arithmetic calculations involved, nothing more, nothing less. Okay, okie dokie. I hope this is clear. Now let me reveal to you the type 6 and the type 7. See, what is type 6? Summation R, NCR and then whole square R going from 1 to n. Summation R, NCR whole square. What is this equal to? This is summation R, NCR into again R, NCR. But I just told you NCR is n upon R, n minus 1 CR minus 1. This R can go here and this is the result which I will be using now 2 times because I have R and NCR into R NCR. So this becomes what? R NCR gives me n into n minus 1 CR minus 1. Again n into n minus 1 CR minus 1. N into n gives me n square, it comes out. Summation n minus 1 CR minus 1, n minus 1 CR minus 1, R going from 1 to n. And now the magic starts, people. Now the magic starts because here I again have product of binomial coefficients. The moment you see product of binomial coefficients inside the series, you should have a big smile on your face because now I know the algorithm. I will be checking whether the sum of lower indices is constant or not. The sum right now is coming out to be 2r minus 2, not a constant. I know how to make it a constant. What will I do? N square as it is, summation as it is, 1 n minus 1 CR minus 1 I will not touch. Other one I will write it as n minus 1 C, n minus 1 minus R plus 1. This will give me n minus R. Now look at the sum. It is R minus 1 plus n minus R. This gives you n minus 1, which is a constant. Okay. Now my sum of lower indices is constant. And you can check all the terms are being exhausted. R is going from 1 to n. So your binomial coefficients, when you open this summation up, when you expand it, you will realize all the terms are being exhausted. N minus 1 C is 0 into n minus 1 C n minus 1 and so on. All the terms are exhausted. So you can apply your shortcut directly. N square as it is, sum of upper indices, which is 2n minus 2, C sum of lower indices. That's it, done, bingo, proved, hence proved. This is your type 6. Summation R NCR whole square is n square into 2n minus 2 C n minus 1. And the last, which is type 7, looks like what? The last result, which is type 7, looks like what? Please check. The type 6 is over. The type 7 comes here. This is summation R into NCR whole square. So previously you have R into NCR complete whole square. Here you just have whole square over NCR. All right. Summation R. Now NCR into NCR. R going from 1 to n. Okay. What is R NCR? I just told you it is n into n minus 1 C R minus 1 and NCR as it is. Now this n will go out. You will be left with n and then multiplied with NCR, n minus 1 CR minus 1, R going from 1 to n. Now you know sum of lower indices this time is not constant, so you will make it constant. You will replace NCR with NCN minus R. When you add now, you will get n minus R plus R minus 1. The sum is coming out to be n minus 1, which is a constant. And all terms are exhausted. So your answer will come out to be sum of upper indices, n plus n minus 1, 2n minus 1, C sum of lower indices. All of this into the n sitting outside. Hence proved. Hence proved, guys. Hence proved. Summation r into NCR whole square is n into 2n minus 1 Cn minus 1. That's how beautifully we are through with our 7 results based upon binomial series. The 7 results based upon binomial series, we are through with all 7 of them. Type 1, 2, 3, 4, 5, 6 and 7. Any confusion, anybody? Any doubt? Any doubt till here? Any doubt? Cool? Done? All these 7 series, why have I shared the proofs with you? Because until and unless you don't remember the proof, you will never ever be able to get confidence over the series. That's for sure. Because still it happens many times with many students I've taught this chapter, this area, this concept of binomial series. Many times students are like, ma'am, so many things we have to remember, so many formulas, so many results. But these 7 results, because we are so much well versed with the proofs, and the proofs are also so simple, 1-liner, 2-liner, much of it goes in the mental math only. Even in the paper, if we forget the result, it takes hardly 15 to 10 seconds for us to prove it. And that's what gives us major confidence during the paper. And that is why you must remember the proofs. You must write the proofs with me in your notebooks as well. Making sense? Now that we are through with all 7 types, let's attack just 2 questions which I have for you based upon type 6 and type 7. Look here, how direct questions come from these type of series. Direct questions. What is written? It's written summation k into 10ck whole square. K going from 1 to 10. It's direct result, guys, direct result. What is summation r NCR whole square? It is n square into 2n minus 2. 2n minus 2 Cn minus 1. That's it. 100 into 20 minus 2, 18 C9. Tell me, if this is clear to you, tell me quickly. If you know the result, this is hardly a matter of seconds to crack this question. Hardly a matter of seconds. This you just have to compare with 22000L, solve and get L. Tell me if this is difficult for you, please tell me right now. Is this difficult? No, right? It's very simple. Very simple. This much to simplification you can very easily do. I don't need to do spoon feeding of this to you, isn't it? Yes? Exactly in the same manner, look at this. JEE Advanced 2018 question, guys. This was JEE Main. Super chindi, super simple. Very easy. Look at this JEE Advanced 2018 sawal. Look at this. 10C1 whole square, 2 times 10C2 whole square, 3 times 10C3 whole square. This is like R times 10CR whole square. Summation R going from 1 to 10. Again, direct, bache, direct. Direct. Summation R into NCR whole square gives you what? N 2n minus 1. 2n minus 1 Cn minus 1. That's it. 10 into 20 minus 1. 19 C9. That's it. This is what is your x. Once you compute x upon 1430 will be your answer. Is this cool? Can you imagine this is a JEE Advanced question? Can you imagine? So never ever underestimate the importance of these results on binomial series. Examiners know this as a matter of fact. If we teachers know it, examiners know it even better than us. That this is an area where maximum students slip and they lose marks. The tendency of students not remembering the type of series or not being able to decode that, okay, this question falls in this type of series category. This is something very common, very common among students. So they are bound to commit mistakes here. And that is what gives leverage to the NTA, to the JEE examiners to set questions from here. Because see, it's an exam of not selecting students, it's an exam of rejecting students. So they are bound to keep questions from this topic. And that is why it is a must for you to master them. Must for you. Alrighty? Alrighty? Now let's get started, people. Let's get started with multinomial theorem. Now, multinomial theorem is very simple. Why is it very simple? And even questions which come from here are very simple. But there is a little catch where students generally get trapped. Now, what is the catch and where do you have to exactly be careful is something which I will explain along the way. But right now, please understand, when you have a binomial expression, that means you have two dissimilar terms raised to the power n, this is binomial expansion. Right? This is binomial expansion. When you have three dissimilar terms, they are being added or subtracted, whatever, raised to the power n, n is a natural number, this is a multinomial expansion. Multinomial expansion. When you have four dissimilar terms, say x plus y minus w minus z raised to the power n, where n is a natural number, again this is a multinomial expansion. So whenever you have more than two dissimilar terms, which you can't combine and make one, whenever you have more than two dissimilar terms forming an algebraic expression raised to the power a natural number, that gives you a multinomial expansion. So how do you expand this? How do you actually perform the expansion? I will not bore you with all of this, but there's just one thing which you must remember, and it is this. I will not bore you with where it comes from because the result itself is super duper simple, guys. Super duper simple. See, how will it look like? I'll write it here only. How will it look like? It will look like x1 plus x2 plus and so on plus xr whole to the power n. This is what? The base is algebraic expression of r dissimilar terms. R dissimilar terms raised to the power a natural number n. This is your binomial expansion. How will it look like? Summation. It's an expansion, right? Summation. What? N factorial upon. You need r constants. Is this cool? Making sense? Is there a lag? Is everything fine now? I guess it's fine. So what I was saying is, this is how your multinomial expansion looks like. This is how your general term in the multinomial expansion looks like. But tell me, how many terms do you think lie in the multinomial expansion? Like when you expand a binomial, when you perform the expansion, binomial expansion, you know if the power is n, there are n plus 1 terms in the expansion. What about multinomial? The power is n, but does that mean that there are n plus 1 terms in the multinomial expansion? No, no, because you have to understand how are the terms being formed. The terms are dependent upon k1, k2, k3 up till kr. The terms are dependent upon k1, k2, k3 up till kr. In how many ever ways you can perform k1 plus k2 plus k3 and so on plus kr equal to n, those many terms are going to exist in the expansion. So, number of cases or number of possibilities or number of solutions of this equation, keeping this restriction in mind, will give me the number of terms in my expansion. Suppose I get one of the possibilities of k1, k2, k3 up till kr, one r values I get, one for k1, one for k2, one for k3 and so on, one for kr, such that each of those values is a non-negative number less than equal to n and their sum is equal to n. I plug in those k1, k2, k3 up till kr values over here and over here. It will give me one term of this expansion. Now I bring another combination of k1, k2, k3 up till kr equal to n. Plug it in the general term, I get another term. Now I take another combination of k1, k2, k3 up till kr up till n. Plug it in my general term, I get another term. So as many as there are valid solutions of k1 plus k2 plus k3 up till kr equal to n, those many terms will exist in the expansion. So what is the answer? How many terms exist in the expansion? As many as there are solutions of these two conditions, or rather as many as there are solutions of this equation keeping this restriction in mind. As many as there are solutions of the equation k1 plus k2 plus k3 up till kr equal to n, keeping the restriction in mind that each of these ki's are actually non-negative whole numbers less than equal to n. Okay? Okay? So how many distinct terms exist in this expansion? This is equal to equal to number of solutions of K1 plus K2 plus K3 up till Kr equal to n, where your K1, K2 and so on Kr are less than equal to n, greater than equal to 0. This is same as saying number of non-negative integral solutions. Is something striking? Non-negative integral solutions of the equation K1 plus K2 plus K3 plus Kr equal to n. And what does this mean? This simply means this is equal to number of ways in which, very interesting, in which n identical objects can be distributed among R boxes such that empty boxes are allowed. Empty boxes are allowed. What is the answer? Yes, very good, Priyanshu. It is n plus r minus 1 c r minus 1. If empty boxes were not allowed, that means inside every box I had to put at least one object, then my answer would have been n minus 1 c r minus 1. Please remember, people have used a very, very important, a short and sweet concept from PNC, which is permutations and combinations. Number of ways in which n identical items can be distributed among R boxes such that no box can remain empty is n minus 1 c r minus 1. And if it is allowed to keep empty boxes, you can even allot 0 items to some boxes, then the answer is n plus r minus 1 c r minus 1. Here 0 is allowed. Do you know? Here 0 is allowed. Why? Because K1, K2, K3 up till Kr are varying from 0 to n. They can take the value 0 also up till n. Okay? And that is why the total number of terms in my multinomial expansion x1 plus x2 plus x3 up till xr raised to the power n is n plus r minus 1 c r minus 1. This is must remember, guys. Must remember. Very good. Is this cool? Now that you understood how a multinomial expansion behaves, what does it look like? How does a general term look like? How many terms are there? What are the conditions, restrictions attached? Let's attack this question. Coefficient of a cube b to the power 4 c to the power 5 in this expansion is what? Come on, tell me. Tell me. What is it? What do you think is the answer? What do you think is the answer? I can understand, Priyanshu, managing your pre-boards, managing your revision, managing your JEE prep at this stage is very difficult. I can very well understand. But it's literally number 1 about prioritizing and number 2 about time management. Please make a very strict schedule. It's not like you are the only student who is here in this situation. Many students have been in this situation in the past. Many will be in this situation in future. Many are in the situation in the current place. But I will tell you that please make a very strict schedule. Prioritize your pre-boards for some time when you're very, very close to the exam. Okay, because it's pre-boards, not even boards. If you really are having that zeal to perform really well in your pre-boards, then definitely as the exams are nearing, give some extra time to study specifically for pre-boards. Okay, streamline your prep towards pre-boards just before the exams. 1 day, 2 days, 3 days before the exams, because you will get gaps as well. In those gaps, you can properly study. And apart from that, you can allot time to your JEE prep, your revision, your formula revision, your PYQ practice, attending these lives. All of that time you can allot to this very strategically. But don't forget to take at least 2 mock tests in a week, no matter what. No matter pre-boards going on, not going on, you can set aside 3 hours to take a mock test. Whatever 2 days of the week you're comfortable with, depending upon your date sheet of your pre-board exams, please take out 2 days to give mock test. Otherwise, you will not even realize you will go behind in the race. And that is something I don't want specifically for you. Okay, fine. You've been studying very hard for a very long time. I would not want you to face any negative outcome. Okay? Yes, 2 mock tests per week, because that will take care of everything. That will take care of you recollecting your concepts. That will take care of you, one second. Yeah, that will take care of you recollecting the concepts, that will take care of you revising, that will take care of you remembering the formulas, that will take care of you recollecting approaches, that will take care of you establishing your familiarity with questions, that will take care of everything related to JEE. Okay, so don't underestimate the power of mock test. Tell me, how exactly will you proceed with this question? See, you have BC plus AC plus AB whole to the power 6. Obviously, the obvious step which should strike your head is multiply by ABC to the power 6 and divide by ABC to the power 6. Why, ma'am? Because you will get A to the power 6, B to the power 6, C to the power 6 outside, and here you will get 1 upon A plus 1 upon B plus 1 upon C whole to the power 6. Very good. But not directly, Priyanshu. Not directly. Because now you tell me, now I'm going to play smart. Why? Because now you tell me I want coefficient of A cube, B to the power 4, C to the power 5. Already there is A to the power 6, B to the power 6, C to the power 6 sitting outside. Whatever terms exist from this expansion, each of those terms will get multiplied with A to the power 6, B to the power 6, C to the power 6. So if I want the coefficient of A cube, B to the power 4, C to the power 5, that means from within this expansion, I want coefficient of A to the power 3, B to the power 2 and C to the power 1. Yes or no? 1 upon A to the power 3, 1 upon B to the power 2, 1 upon C. This is what I want. Because whatever term has this, it will get multiplied with A to the power 6, B to the power 6, C to the power 6. So eventually you will be left with A to the power 3, B to the power 4, C to the power 5, which is what I want. And that is why from within this expansion, this is to chalo, constant quantity sitting outside. But from within this expansion, I want the coefficient of 1 upon A cube B square C. Remember, I want the coefficient of 1 upon A square B cube, A cube B square into C. Cool? Now let's start. 1 upon A plus 1 upon B plus 1 upon C raised to the power 6. How do you write the general term? How do you write the general term? Now you will write the general term. How do you write the general term? 6 factorial upon, there are 3 dissimilar terms, 1 upon A, 1 upon B, 1 upon C. So K1 factorial, K2 factorial and K3 factorial, correct? 1 upon A raised to the power K1, 1 upon B raised to the power K2, 1 upon C raised to the power K3. Is this making sense? Is this making sense? Now what you'll do? Remember the restriction. K1, K2 and K3 are less than equal to 6, greater than equal to 0. And another even important restriction is that the sum is equal to the final index, which is 6. Cool? Very good. Very good. Now what do you want? You want the coefficient of 1 upon A raised to the power 3, 1 upon B raised to the power 2 and 1 upon C raised to the power 1. That means you want K1 to be 3, K2 to be 2 and K3 to be 1. In that case, the coefficient will come out to be 6 factorial upon 3 factorial, 2 factorial, 1 factorial. Yes or no? This is 6 into 5 into 4 into 3 factorial upon 3 factorial into 2. This gets cancelled out. This is 30 into 2, which is 60. Okay, so the coefficient of 1 upon A cube B square C was 60, which got multiplied with this. So eventually you are getting coefficient of A cube B to the power 4 C to the power 5 is 60. Is the logic clear? Is the logic clear? It's hashtag HDCC. It's not 120, it's 60. Okay? Okie dokie? Moving ahead, what is the total number of distinct or dissimilar terms in this expansion? Tell me. When you look at this, this is made up with 4 dissimilar terms, right? This is equivalent to saying x1 plus x2 plus x3 plus x4 whole to the power n. So the value of r is 4 and n to chalo is given to you. How many terms will be there in this expansion? Last mein mistake kar di. Okay, no issues. How many terms will be there in this expansion? This is equivalent to saying that you have n identical items and you want to distribute it among 4 boxes such that empty boxes are allowed. Such that empty boxes are allowed, the answer is n plus 4 minus 1, C4 minus 1. So this is n plus 3, C3. That's your answer. Very good. So questions like these also can directly come in the paper. You must remember the logic, the concept. Very good. Come here now. Very interesting question. Very interesting question. What does it say? In this expression, how many are the number of rational terms and what is the sum of rational terms? So I have to totally compute rational terms. Any term in this expansion will look like what? Baba, any term in this expansion will look like what? Huh? Any term in this expansion will look like what? General term. 10 factorial upon k1 factorial, k2 factorial, k3 factorial, 2 to the power 1 by 2 raised to the power k1, 3 to the power 1 by 3 raised to the power k2, 5 to the power 1 by 6 raised to the power k3. Now, don't forget the restriction upon k1, k2, k3 is it's less than equal to 10, greater than equal to 0 and the sum is equal to 10. Very important restrictions, guys. Very important. If you take these restrictions lightly, your answer can go south. Literally, your answer will go south. You will land up with a very incorrect answer. So don't forget to keep these 2 restrictions in mind always. Perfect. Next what? If I want a rational term, I want what? 2 to the power 3 to the power, 5 to the power. These terms completely I want rational. When will they turn out to be rational? When the power is a whole number. Yes or no? Say rational terms or say integral terms. When will this come out to be an integer? Each of these. When the power is a whole number. So what I want is for rational terms. For rational terms, please understand very carefully. It's very important. For rational terms, I want k1 by 2 to be a whole number. I want k2 by 3 to be a whole number. I want k3 by 6 to be whole numbers. Very good. This implies I want k1 to be a multiple of 2. It can be 0 or 2 or 4 or 6 or 8 or at max 10 because k1 can be at max 10. Similarly, k2 can be at max 10, k3 can be at max 10. K2 has to be a multiple of 3. It will be 0, 3, 6 and 9 and k3 has to be a multiple of 6. So 0, 6, 12. 12 is not allowed because k3 can be at max 10. So these are all the possibilities of k1, k2, k3. Now what do I need? I want k1 plus k2 plus k3 equal to 10 as well. Which combination to take of k1, k2, k3? That will be taken care of by the condition that the sum should be equal to 10. So let's start. Case 1. If your k3 is 6 or rather 0, k3 can be 0 or 6. Least number of possibilities are for k3, 0 and 6. So let's start with k3. That's the case 1. Very good. Very good. Is this clear? What did I say? A general term in your multinomial expansion here looks like this. If you want this term to be rational, this part to chalo is fine. 10 factorial upon any number, whatever it comes out will be a real number. It will be rational only, not irrational. It will be rational. But what about this part? 2 to the power something will be rational when that something is a whole number. 3 to the power something will be rational when that something is a whole number. 5 to the power something will be rational when that something is a whole number. So these powers have to be whole numbers. k1 by 2, k2 by 3, k3 by 6. For k1 by 2 to be a whole number, k1 has to be a multiple of 2. But k1 is allowed to sandwich between 0 and 10. So k1 can be 0, 2, 4, 6, 8, 10. Similarly, k2 has to be a multiple of 3, but k2 is only allowed to be sandwiched between 0 and 10. So k2 can be 0, 3, 6, 9. k3 has to be a multiple of 6, but k3 is only allowed to be sandwiched between 0 and 10. So k3 can be 0 and 6. Now I want some combination of k1, k2, k3 from here, which also satisfies k1 plus k2 plus k3 equal to 10, because then only it will be acceptable, otherwise it won't be acceptable. Okay, so I'm starting with k3 0. If k3 is 0, I know k1 plus k2 plus k3 is 10, but k3 is 0. So that means I want k1 and k2, so that k1 plus k2 is 10. So from here, how can you get k1 plus k2 10? When k1 is 10, k2 is 0. When k1 is 10, k2 is 0. Or when k1 is 4, k2 is 6. When k1 is 4, k2 is 6. Any other possibility of getting k1 plus k2 10? No, no possibility. That's it. So you have two terms coming from here. What are the two rational terms? 10 factorial upon k1, k2, k3. k1 is 10, k2 is 0, k3 is 0. Okay? 2 to the power k1 by 2. k1 by 2 means 10 by 2. 3 to the power k2 by 3. 0 by 3 is 0. 5 to the power k3 by 6. 0 by 6 is again 0. This is one term. This is one term, rational. Another one will be 10 factorial upon k1 factorial, k2 factorial, k3 factorial. 2 to the power k1 by 2. 4 by 2 is 2. 3 to the power k2 by 3. 6 by 3 is again 2, and 5 to the power 0. These are your two rational terms in the expansion. These are your two rational terms in the expansion. What about case 2? When your k3 is 6 fixed, in that case k1 plus k2 will have to be 4, so that the total sum is 10. Now what are the possibilities from here of k1 and k2 to give me the sum of 4? If k1 is 0, no. If k1 is 4, k2 is 0. That's it. If k1 is 4, k2 is 0. That's it. So from here I am only getting one term, 10 factorial upon k1 factorial, k2 factorial, k3 factorial. 2 to the power k1 by 2, 3 to the power k2 by 3, 5 to the power k3 by 6. Okay, this is one rational term, another rational term, another rational term. Total number of rational numbers is 3 and not 4. And when you add all of them, your answer will come out to be 11792. So B and D are the right options. Very good, Priyanshu. Not A, not C. Is this question understood? Is this question understood? Very nicely. Any doubt, any confusion, any problem, please stop me right now. Please stop me right now. Stop me right now and ask me if there's any doubt, any confusion. Is that cool? Everything okay? We shall move ahead. All right. Now tell me, what is the coefficient of x to the power 7 in this expansion? What is the coefficient of x to the power 7 in this expansion? And here is where the catch comes into action. Here is where the catch comes into action. What is the catch? I want you to recognize the catch. I want you to recognize the catch because here it says coefficient of x to the power 7 in this expansion. Now look here carefully. It says 1 plus 3x minus 2x cube whole to the power 10. N is 10. N is 10. But how will you write the general term? The general term, bache, will look like 10 factorial upon k1 factorial, k2 factorial, k3 factorial, 1 to the power k1, 3x to the power k2 and minus 2x cube to the power k3. Now you simplify this general term to such an extent that all the constant parts get separated, all the variable part gets separated. So you will get 10 factorial upon k1 factorial, k2 factorial, k3 factorial. 1 to the power k1 is 1 only, 3 to the power k2 minus 2 to the power k3, x to the power k2 plus 3k3. There is no role of k1 here. No role of k1 from here to here. This is completely the constant part and this is only the variable part. This is only the variable part. I want coefficient of x to the power 7. That means I want k2 plus 3k3 to be 7. I want k2 plus 3k3 to be 7. This is one thing that I want. I also want to adhere to the condition that k1 plus k2 plus k3 is equal to 10. And I also have to keep in mind that my k1, k2, k3 do not exceed 10 and that they are non-negative. This is where multinomial theorem traps students, because now you have to work with cases. If you miss out on even a single case, flop. The strategy is flop. So what to do? K2 plus 3k3 is 7. So let's start k1, k2, k3. How many values, what all values can I accept? 3 times k3 is the largest, right? So let's start with k3 being 0. If k3 turns out to be 0, k2 plus 0 equal to 7 gives me k2 as 7. But k1 plus k2 plus k3 is 10, that gives me k1 as 3. One possibility done. What if k3 is 1? If k3 is 1, you get k2 plus 3 is 7. So k2 comes out to be 7 minus 3, which is 4. 4 plus 1, 5. K1 is 5. What if k3 is 2? You get 6. 7 minus 6. 7 minus 6 gives you 1. 2 plus 1, 3. K1 comes out to be 7. What if k3 is 3? 3 into 3, 9. 7 minus 9 will give me minus 2. K2 cannot be minus 2. No. Stop here. That's it. That is it. That is it. So you have three coefficients of x to the power 7. Add all of them and get the answer. 7, 1, 2, very good. 5, 4, 1, very good. 3, 7, 0, very, very good. That's it. So what is your answer? 10 factorial upon k1 factorial, k2 factorial, k3 factorial. 3 to the power k2 into minus 2 to the power k3. So 3 to the power k2 minus 2 to the power 0 is 1 only, plus again 10 factorial upon k1 factorial, k2 factorial, k3 factorial, 3 to the power k2, 3 to the power k2 and minus 2 to the power k3, plus again 10 factorial upon 7 factorial, 1 factorial, 2 factorial, 3 to the power k2 minus 2 to the power k3. This is your answer. The only problem with this approach is you have to be very conscious that you don't miss out on even a single case. If you miss out on even a single case, the question is gone. Add all the 3 things and you get the answer. Now what happens? I'll give you a good news now. What happens many a times the question looks like it's of a multinomial expansion, but it's possible to crack it using binomial approach. And whenever it is possible to crack a multinomial question using binomial approach, you must do that. Because in the multinomial approach, it's not very difficult, but the only catch or the slippery area is that there are cases involved. If you miss out on even a single case, the question is gone. But in binomial, you always get a short answer. Okay, there are no cases as such involved. And it's very easy for you to deal with binomial because you can open up the entire expansion, see each and every term, and then figure out the analysis that, okay, what will take place, what will not. But in multinomial, you can't see the entire expansion, no. So a lot of cases work has to be done, which becomes pretty tricky. Like for example, very good, very good Priyanshu. For example, this is multinomial, but I will not solve it using multinomial. I will simplify this expression 1 plus x square common 1 plus x whole to the power 11. This will give me 1 plus x into 1 plus x square whole to the power 11. So it's the product of, this is nothing but product of 2 different binomial expansions, na bachche, which is a much easier life for me, baba. It's way easier life for me now. Why? I will open it up. I will see all the terms by expanding it up fully. No problem at all. I will get 11c0 plus 11c1x plus 11c2x square plus 11c3x cube plus 11c4x to the power 4 plus and so on 11c11x to the power 11. What about the next expansion? This will be 11c0 plus 11c1x square plus 11c2x square whole square, which is x to the power 4 plus 11c3x square to the power 3, which is 6 plus and so on. Now, how will you get x to the power 4? See, 11c0 into 11c2x to the power 4. So, 11c0 into 11c2, one of the coefficients. 11c1 should be multiplied with x cube, but there is no x cube term in the next bracket. So, this is gone. 11c2x square into 11c1x square. Perfect. 11c2 into 11c1. 11c3x cube has to be multiplied with something into x, but there is no x term in the next bracket. So, this is gone. 11c4x to the power 4 into 11c0. Perfect. 11c4 into 11c0. That's it, guys. This is my answer. That's it. That's how easy life becomes when you are able to dissolve your multinomial into product of, let's say, 2 binomials or 3 binomials. Because the profit is, number one, you are comfortable with binomial. You've studied and spent time with it way more than multinomial. Number two, it's possible for you to expand the entire binomial expansion and see each and every term. Once you're able to see it, the chances of you committing mistake become supremely less. But in multinomial expansion, you're not able to see all the terms. And when you don't see all the terms, imagining cases, trying to visualize what will happen or not, in that pressure situation of examination becomes quite risky. The stakes are too high. The stakes are too high. Got it? For example, I'll share with you another question. Look here. What is the coefficient of x to the power 4 in this expansion? Very simple, very nice question because it looks like multinomial. 100%. 100%. 100%. Looks like multinomial. But I'm going to solve it using binomial. How? See, 2 minus x plus 3x square whole to the power 6. Is this making sense? Making sense? This is one of the terms. This is another term. That's it. My perception is that yes, it is looking like 3 terms, but I have made it in such a way, written it in such a way that now the expression is a binomial expression. Raised to the power 6 is a binomial expansion. Cool? Cool? Okay, let's open it up. Let's open it up. 6c0, 2 minus x to the power 6. 6c1, 2 minus x to the power 5 and into 3x square to the power 1 plus 6c2, 2 minus x to the power 4, 3x square to the power 2. I want coefficient of x to the power 4, remember. Next, 6c3, 2 minus x to the power 3, 3x square to the power 3 plus and so on. I don't need to write any term further. From here, what will I get? See, 6c0 as it is. Cool, 6c0 as it is. From this binomial expansion, I want coefficient of x to the power 4. From this binomial expansion, I want coefficient of x to the power 4. Please make sure you understand that in 2 minus x to the power 6, how does the general term look like? 6cr, 2 to the power 6 minus r minus x to the power r. That means 6cr, 2 to the power 6 minus r minus 1 to the power r, x to the power r. If you want coefficient of x to the power 4, it will be 6c4 2 to the power 6 minus 4, which is 2, minus 1 to the power 4, which is 1. That's it. That's it. This is the coefficient of x to the power 4. Okay, cool. Plus, next, 6c1. 6c1 is 6 into 3 into x square is written and then 2 minus x to the power 5 is written. That means what? What is my variable part? This completely is my variable part. Now look here. How will a general term look like? 5cr 2 to the power 5 minus r minus x to the power r into x square. Yes, no? This gives you 5cr 2 to the power 5 minus r minus 1 to the power r x to the power 2 plus r. Now, if you want coefficient of x to the power 4, you want 2 plus r to be 4. That means r is 2. So, what is the coefficient? Coefficient is 5c2. 2 to the power 5 minus 2 gives you 3, minus 1 to the power 2 is 1, x square. So 5c2 into 2 cube. 5c2 into 2 cube. From here, you get 5c2 into 2 cube as the coefficient. Into 6 into 3 is already written. Is this clear? Is this clear, yes or no? 5c2 into 2 cube. Is this clear? Yes, ma'am, no, ma'am? Yes. Up next. Let's go to the next one. This one. Okay, plus 6c2 as it is, 3 square 9 as it is. Constant part I am just removing. I am left with x to the power 4 into 2 minus x to the power 4. If x to the power 4 is already sitting outside, from 2 minus x to the power 4, I only want coefficient of x to the power 0. From here, I want coefficient of x to the power 0. What will it look like? 4c0, 2 to the power 4 minus 0. Coefficient of x to the power 0 I want. General term look like 4cr, 2 to the power 4 minus r, minus 1 to the power r, x to the power r. If you want coefficient of x to the power 0, it will be 4c0, 2 to the power 4 minus 0, minus 1 to the power 0, which is 1, into x to the power 0. So 4c0 into 2 to the power 4. See, 4c0 into 2 to the power 4. That's it. Beyond this, you will not get coefficient of x to the power 4 at all. Beyond this, you will not get. Beyond this, you will not get. So your answer is 6c0 into 6c4, 2 square, plus 6 into 3 gives you 18, into 5c2 into 2 cube, plus 6c2 into 9, into 4c0 into 2 to the power 4. Perfect. Cool? This is your answer. So this is how, yes, you could have proceeded with the multinomial approach. I am not against it, but I am just saying this for your safety, utmost safety. What safety? What safety? That in multinomial, because you are not able to see all the terms sitting in the expansion, determining correct cases, correct number of cases becomes a little bit of a task in that pressure situation. It might happen that you are so stressed that you miss out on any one possibility, any one case, any one combination, and that's why your answer gets hampered. It comes out to be wrong. But in the case of binomial, what is the profit? That number one, you are super comfortable, you spent tons of time with it. Number two, you are able to see all the terms in the expansion because you know what the terms look like in a binomial expansion. It is super simple for you to expand it, no? And once you're able to see the terms, then figuring out what gets multiplied to what to give you my desired outcome is very simple, very easy, something you're super comfortable with. Okay, so always remember, if possible, don't go for multinomial, go for binomial. Break it up into 2 binomials or 3 binomials, sum of 3 binomials, product of 2 binomials, whatever. But if this is not happening, then of course go ahead and do questions with the multinomial approach. I've shared both of them with you. Okay, fine. This is the last topic, guys, which is greatest coefficient. Questions from here directly come based upon the formula. There's only one formula which you have to remember by heart. What is the formula? In the multinomial expansion, what is the greatest coefficient? Now, when you say greatest coefficient, you already know what does that mean. When you write each term in the multinomial expansion, there is a constant part to it and a variable part to it. If you assign a specific value to the variable, then each term on solving will come out to be a real number. And out of all the real numbers, which are now the terms, what is the greatest term? Is what I mean. What is the greatest term? And when you say greatest coefficient, what does that mean? That you are assigning the value of the variable to be 1. The moment you assign variables value to be 1, all you are left with is just the coefficients. And then all the coefficients are real numbers. You can easily compare which is the greatest one or the largest one numerically, mod wise. But this formula gives you direct answer for greatest coefficient. It is n factorial upon q factorial to the power r minus k upon into q plus 1 factorial raised to the power k. What is q? Q and k. Q is the quotient, k is the remainder when n is divided by r. So this is n, this is r. You take n, you divide by r, q comes out to be the quotient and k comes out to be the remainder. Okay? For example, see, what is the greatest coefficient in this expansion? Now here n is 15 and your r is 4. N is 15, r is 4. When you divide 15 by 4, you get 4 into 3, 12. and this is 3. So 3 is your Q, and with that it's a wrap, people. It is a wrap. Why is this a wrap? Because we're through with binomial completely. We're through with binomial completely. And I want you to please take a note of this, that each and every subtopic which is there in binomial relevant to your examination has been done. There are some questions which specifically, deliberately I have not discussed because I want to discuss them in the question series. So here my target was to explain all the concepts to you with utmost clarity, all the cases, all the possibilities which can exist for a certain concept. I have explained it to you. I hope you understood very, very nicely. Very, very, very nicely. If there's any doubt, let me know in the comments. Don't forget to join my Telegram channel, which is Study with Bhoomika Ma'am. Okay, I'll be sharing the notes there itself. And also I'll be sharing some very nice questions which you will be able to crack, because now you understood the entire concept of binomial. And also those questions will make you brainstorm. Those questions will help you apply these concepts which you've learned. And those questions will help you establish a firm grip over binomial. Okay? So if there's any other request, any other request, any problem area which you want me to address in math, let me know in the comments below. And for now, it's me, Bhoomika, signing off.